haloarenes. Let us take up the chemical properties of haloalkanes for discussion. Look at these reactions. This is the one we already used for the preparation of haloalkanes from alcohol. And this reaction is the reverse of this, exactly reverse of this reaction. Because why I am taking these two reactions? Look at this reaction. It is taking place under drastic conditions like concentrated HCl and anhydrous zinc chloride. But this reaction is not taking place under such conditions, normal conditions. Shows that this is reactive, this is less reactive. The chemical bond, this is called hydrolysis of water, of course. This chemical bond is weaker, this chemical bond is stronger. Stronger the chemical bond, less reactive. Weaker the chemical bond, more reactive. Among them, notice that this is more reactive than this. And when I talk about the reactivity of the haloalkanes, they are reactive compounds. They are more reactive compounds. And the number of chemical reactions, there are types of chemical reactions. Among them, one is nucleophilic substitution. That is, one nucleophile is replaced by another nucleophile. And this involves two different mechanisms. In these cases only, there are two different mechanisms. There is SN1 mechanism and SN2 mechanism. But the reaction remains same. Reaction remains same, but the mechanisms are different. What are these mechanisms? The mechanism is based on the steps of reaction involved and kinetics. What kinetics, what steps are involved in the reactions, but reaction remains same. Different steps and kinetics are different. Chemical kinetics. Let us look into the mechanism of this SN1. I will briefly go through this mechanism, SN1 mechanism. Here this is RS, that is haloalkanes, alkyl halide. Here alkyl halide. Here the chemical bond in this mechanism, this chemical bond completely breaks, dissociates into the corresponding ions, that is plus and minus, unsymmetrical breaking. This is called carbocation, this is halide, next minus. And after this step, this carbocation is attacked by water, nucleophile. That is, of course, neutral nucleophile. Nucleophile, because of presence of this lone pair of electrons in the oxygen, this lone pair can attack the positive charge of the carbon, forming chemical bond like this, resulting in, that is, shifting of plus charge from the carbon to oxygen. And this is unstable, again you get this, this is unstable. This undergoes further rearrangement. That means this chemical bond breaks, takes back this electron, pair of electrons, to nullify the positive effect, and this H is removed as H plus. The H plus and X minus becomes HS. Then ROH, alcohol formation. These are the steps of reaction. And in this, the mechanism, the steps are different. Here, what is the step here? That is alkyl halide, the same type of compound. But it is not the breaking of the chemical bond. The chemical bond will not dissociate into anion and cation like this. It is the attack of this is nucleophile, oppose negative charge. The charge is ionic nucleophile. It attacked this carbon of the R2 from behind, but it cannot attack from because already bond is there. This bond is not breaking. Now when attack from this begins to form new chemical bond. Once the new chemical bond begins with this chemical bond begins to break. Not straight away breaking away. With this attack, chemical bond begins to break. Resulting what is that? A partial this chemical bond is partially formed, this chemical bond is partially broken, and forming a complex known as activated complex or intermediate complex. Look at the difference. The intermediate compound is this, intermediate compound is this, carbocation. This is activated complex, intermediate complex. This follows theory of what is that activated or absolute reaction rate. Now this is reversible with this. That is, can go back or we can proceed like this. So now it depends on the stability of this complex. It depends on the stability of the carbon cation. When the intermediate, now it is decomposed into this and this. Now as the bond becomes stronger and stronger, it breaks away as X minus, becomes OH or alcohol. It is replaced by OH minus. Finally, these are the steps involved. It follows theory of what is that activated complex, intermediate formation. This is carbocation formation, intermediate. On the basis of the steps, we can read the chemical kinetics or kinetics of these reactions. There are different steps are there. 3 steps are there. This step is the slowest step. Because in accordance with the chemical kinetics, rate of reaction is equal to rate constant of the reaction into concentration of the reactants. Here in this step only one reactant is there. This reactant is not seen, comes in the next step. Therefore, rate of reaction is not depending on the concentration of water, it is depending on the concentration of halide only. So concentration to the power of 1, here concentration to the power of 0. And the order is sum of these two exponents. Order of the reaction is equal to 1 plus 0 is equal to 1. First order reaction, this one stands here as 1. 1 stands in the first order reaction or unimolecular reaction. This one mechanism. Unimolecular nucleophilic substitution. What is SN2 mechanism? In this steps of reaction, rate of reaction depends on this. So rate of reaction is equal to rate constant into concentration of this reactant and concentration of this reactant. This reactant is nucleophile, that is to the power of 1 to the power of 1. Now the order of reaction is equal to 1 plus 1 is equal to 2. Order of reaction. This 2 stands for, that is 2 stands for 2 mechanism. So first second order or bimolecular nucleophilic substitution. That is why in accordance with the steps and the kinetics, the mechanisms are named as SN1 mechanism and SN2 mechanism. Now why this SN1, the mechanisms are different even though reactions are same? It is some factors, that depends on some factors. Some factors will favor this reaction, some other factor will favor this reaction. What are the factors? To talk about the factor, look at the reactants, what reactants we are using, halide. So it depends on what type of alkyl halide is involved and what type of halogen atom is involved. That is also important. And involves nucleophile. Nucleophile. What type of nucleophile is involved? And also the reaction is not taking place in a solvent, in a liquid medium, in particular solvent. Therefore, This mechanism depends on what kind of solvent you are using, and this also what kind of solvent will favor this reaction. Let us discuss one by one. Discuss the nature of alkyl halide. What kind of alkyl halide will favor this mechanism, and what kind will favor this mechanism? Look at this alkyl halide in this carbocation formation. This carbocation formation here, that is one chemical bond is broken, 3 remains chemical bond. Here chemical bond with different groups. Here 3 hydrogen atom, methyl, 2 hydrogen, 1 methyl. Here 2 methyl, 1. All of them are methyl. Of course, this carbon is, that is tertiary. This carbon is secondary. This carbon is primary. This carbon is methyl. This also called primary like that. Now look at that substituent. What is that? The carbocation here. After the dissociation, this carbocation should be stabilized. What is the condition for stabilizing carbocation? The stability is what is that? Inductive effect like this. Positive inductive effect of the substituent group. These are known as substituent groups. These are known as substituent groups. I have written like this. Here they have positive inductive effect. They can push the electron. This substituent can push the electron, sigma bond electrons to carbon. Electron donating, electron pushing towards this. This pushing or positive effect will, what is that? Stabilize the carbon, because positive, if the electrons are pushing, what is that? Stabilize the carbon, carbocation. Stability increases. It depends on the stability of carbocation. Very important. This reaction depends on the stability of the carbocation. The stability of the carbocation depends on the plus I effect of the substituent. If there is more plus I effect, this mechanism is favored. That is CH3 I effect, H is I effect, but it is more, but is very less I effect. Where there is plus I effect is very less, will not follow this kind of mechanism, that is other mechanism. Where this follows this mechanism, what is more I effect, will follow what is that? SN1 mechanism. Group like this, electron plus I effect, methyl more plus I effect, and even more plus I effect is because of ethyl group. If there is ethyl group, it is more effective, plus effective. So that is even more further stabilized, favor the SN1 mechanism. That is what? For the condition required. But here the intermediate formation is activated complex. Activated complex. Here no carbocation formation. That is why. This activated complex, what is that? Formation will not favor by plus effect. It is favoring by minus I effect. That is, activated complex is more stable. It stabilizes. If the substituent group have less I effect like this, or minus I effect, that is electron withdrawing group, not electron donating group. So electron withdrawing group is like this. CH3COC, that is acetyl group. So the acetyl group is electron withdrawing group. So in place of CH3, if you have CH3, COCH3, COCH3 becomes what is reverse, minus inductive effect. That kind of substituent will favor this mechanism. That kind of substituent will make the activated complex more stable and favor this. So example like this is less pressure, the carbocation like this will favor SN1, SN2 mechanism. But carbocation like this will favor SN1 mechanism. This will favor SN4 mechanism. That is accordingly the arrangement, what is that? Alkyl, depends on the nature of alkyl halide. Here that is degree of favorism, what is that? 3 in this order. and plus I effect, that is steric hindrance, that is bulky group. Bulky group will have steric effect. And in SN1 mechanism, presence of SN2 mechanism, presence of bulky group surrounding this carbon will not allow OH to attack the carbon. That will hindrance. That is why we need group like this hydrogen. That is small group can attack from this side. There is space available, it can attack from this side. But bulky group, the hindrance will not favor SN2 mechanism. So that is what we have the conditions. It is favored by this methyl, that is this and this more favorable for this. In this case, this and this more favorable. In addition to this, plus I effect plays an important role. Minus I effect plays an important role. So that is what the alkyl halide, the nature of alkyl halide, and the presence of substituent in the what is that carbocation? There is carbon, simple carbon, plays an important role. And next is nucleophile. What kind of nucleophile? Here, nucleophile like this. That is a weak nucleophile. The nucleophile like this, strong nucleophile. This mechanism requires strong nucleophile. The attack from break. That is only when it's attacked, chemical bond breaks. So it always requires a strong nucleophile. But this attack, what is not, even a weak nucleophile like this, water and methanol, here they have lone pair of electrons in the oxygen, lone pair of electrons on this oxygen. This can attack, that is, can favor, do the process like this. But doesn't require nucleophile strong. But this requires very strong nucleophile. What are those strong? There are a number of nucleophiles, strong nucleophile. Hydroxyl, Cl, cyanide, SH minus. You know this. O and S are same periodic group. That is why like this, SH minus, and OPH, that is phenol is benzene structure. Phenol, derivative of phenol. That is O phenol. That is S is same like this, S. CH2 minus, ammonia and amine. That is neutral, they are ionic. These are strong nucleophile. These nucleophile can favor SN2 mechanism. This kind of mechanism, nucleophile. Another point about the halide. Here the chemical bond breaks in this mechanism. Chemical bond breaks, completely breaks. So for breaking of condition, for the breaking of chemical bond, it requires one condition. What is the condition? The halogen should be a good leaving group. So among the different halides, that is Ri, Br, I is a very good leaving group, and F is a poor leaving group. The order of what is that group, that is halide, which leaves easily, breaks chemical bond and go away like this. Depends on this. That is I will favor. That is I and Br usually favor this mechanism. Very good leaving groups. It is bigger in size and chemical bond breaks easily and it can go away. Whereas Cl and F, small size and the bond, negative, more negative, electronegative, bond is strong, cannot move away, cannot break away easily, requires strong electrophile like this to break the chemical bond. That is why these, what is that, F and Cl usually favor SN2 mechanism. That is depending on the nature of halide. You can see different types of mechanism. And last one, very important, solvent. Because these reactions take place in a liquid medium, in one particular solvent medium. Here there are two different types of solvents. We have polar solvent, It requires polar solvent always. The reason, this chemical bond is polar. This chemical bond is polar. So to break the chemical bond, polar chemical bond, very easy to break. Only in presence of what is that? The medium, the solvent, which is polar. Polar solvent will favor the breaking of chemical, because in both the cases chemical bond breaks of course, one or the other way. We need polar, polar. Difference is protic, aprotic. What is protic? Protic means this solvent contains some amount of H plus ions. Some molecules dissociate, give H plus ions, because the replaceable H plus ion, replaceable H plus ion, H plus and H plus ion. Some amount of H plus ion is there. And this is diagonal, this favor, it is highly polar. But these are polar, not containing replaceable hydrogen like this. Aprotic, this usually not containing any kind of H plus ions. Next one. So example, acetone, organic solvent. Here, DMSO abbreviation, dimethyl sulfoxide, S double bonds, yes, this is. And one more, this is amide, that is formaldehyde amide, formamide, dimethyl formamide. And one more, ROR ether. These solvents are aprotic, not containing any kind of H plus ions, but polar. These solvents will favor this reaction, this mechanism, because after the bond breaks into two ions, that is carbocation and anion like this halogen, that is halogen anion, this is stabilized by the presence of the group, that is substituent. Now this requires some kind of stability in the solvent. It is stabilized by solvation of this proton, that is H plus ions, protic. H plus ions are, so it is stabilized, that is what is that, a layer that is surrounding this, and avoid what is that, back reaction after the point. That is stabilizes. It is stabilized by substrate group. That is the one. That is the criteria is required. So polar protic solvent will favor this mechanism. But this mechanism requires polar, non-protic, because here it is not dissociating separately. It is only dissociate at the end. Doesn't require the ions like this in the solvent. That is aprotic. So polar aprotic will favor the mechanism like this, eccentric mechanism. So these four important factors plays an important role, whether the reaction undergoes this mechanism or this mechanism. So with this, let us look into that last one. If this mechanism takes place, what kind of configuration we get? Because the geometrical configuration of molecule also important. With this mechanism, what kind of configuration we get? So with this mechanism, here chemical bond breaks forming carbocation. So initially there are four chemical bonds, of course with halogen. If there are four chemical bonds, then what is that? The geometrical arrangement will be tetrahedral fashion. There is a tetrahedral geometrical arrangement of chemical bonds. Once this chemical bond is broken, that is removed, then remains only three chemical bonds, carbocation. What would be the expected geometry? It should be a planar, not tetrahedral. We will go to a planar structure like this. Though carbocation is planar, if it is plane, means carbon in the plane, the center. So this carbocation can attack either from the upper side or from the lower side. What attack? Nucleophile. There are two possibilities. So if attack from the upper side, it forms one configuration. If attack from the lower side, forms other configuration. That is why we have two possibilities. So attacking from one side, that is upper side, the configuration is retained. Attacking from the other side, configuration is inverted. Look at the tetrahedral geometry. Tetrahedral geometry. This is retention, this is inversion. Both are possible, 50-50, equal. So in this mechanism, we have equal mixture of configuration. There is a mixture of configurations in equal amounts. If it is R and S configurations. If the carbon is chiral, what is chiral? If the carbon is connected by 4 different groups, it becomes a chiral carbon, asymmetric carbon, becomes enantiomers, 2 different enantiomers. If one is R configuration, other is S configuration, that is 50-50. So mixture of configuration in SN1 mechanism. But in SN2 mechanism is only one configuration, that is inverted, because here the attack is from the back side, exactly opposite direction. It cannot attack from this side because already chemical bond is here. It can attack from the back side. With this attack, what is that? Chemical bond is forming this direction and is removed. What is that? That is removed and all this chemical bond remain adjusted. Begins to form, begins to breaks away, and chemical bonds with this assignment. This configuration will take place. Exactly inverted. If this is in one direction, this is in the opposite direction, the product. So here the geometrical configuration is inverted. If the reactant is R configuration, it is S configuration. Completely inverted. So that is the kind of configuration expected from this central mechanism. This is regarding the SN1 and SN2 differences, that is factors which favor, and what is the geometrical configuration we expect in case of SN1 and SN2 mechanism. That is about this. With this knowledge, let us move on to the examination corner. These are the examples that is already asked in the examination, either in main exam or in the CET like this. Look at the compound. Here carbon is here. Carbon is here. Tetrahedral. What is that? Carbon. There are 4 chemical bonds. Chlorine, the hydrogen. Here this hydrogen is deuterium. Isotope. Hydrogen. Here this also hydrogen. Tritium. Isotope of hydrogen. It contains one proton, contains one proton, neutron, one proton, two. That is only one electron only. That is Cl. When you look at this configuration, always higher or lower. This is T. That is Cl with about this chemical bond, and then these 3 are in play. That is why higher order priority. First this and this. That is R configuration, right direction. Now, this undergoes what kind of mechanism? In presence of this reagent, look at that reagent will make the difference. KOH, it is strong, strong nucleophile. And this solvent, DMSO, that is dimethyl sulfate. This will favor SN1 mechanism. That is why we were inverted. That is, if Cl is here, this side will come. We need to change. That is the configuration. So if it is R means it is S. That is configured is not T. That is higher order. This is T and next D and H. S configuration. So R becomes S by SN2 mechanism. That is the correct picture. Now the second example. There is one more symbol to be remembered. What is the symbol? Here this is CH2, CH, CH2. That is the way. And one more here, the line, thick line with this. And dotted line like this. Shows that very important. If thick line is one configuration, dotted line is the other configuration. That is configuration inverted. Same thick line retention, that is same side. Dotted line is exactly opposite side. That is a symbol need to be remembered. Very important. Another symbol in chemistry. Usually write no inverted no retention inversion always in this thick line and dotted line like this. In exam also and also books also written like this. That is why here secondary carbon with this reagent, this can undergo both type of mechanism possibilities. Both type of because depends on this condition, that is the nucleophile and the solvent. Secondary carbon depends on the nucleophile and the solvent. If this nucleophile is strong, this is solvent. Dimethylformamide solvent. So what is that? SN2 mechanism. That is only one carbon inverted. Here Cl is replaced by Cn nucleophile. Configuration is inverted. This is the correct configuration for this. If this is H2O, can also react with H2O. The mechanism is different. That is SN1 mechanism. SN1 mechanism are two configurations reacted. One is same configuration, retention. That is here in this water is act as a solvent as well as a nucleophile. Can donate OH minus. That is OH. Retention and inversion. SN1 mechanism. This is the correct answer. So the reactivity of this with H2O is this. Reactivity of this with this is this. These are already asked in the examinations. Next is allylic group. CH2, CH, CH2 here, Br. Here carbon is primary carbon. This carbon, because presence of this group, will make two types of mechanism. It has undergone both SN2 mechanism and SN1 mechanism. Look at this. This carbon is original electron withdrawing group because presence of double bond usually electron withdrawing group or undergo resonance to stabilize the carbon. Either way. That is why in presence of strong electrolyte undergo SN2 mechanism inverted. Here inverted. In presence of the solvent, that is CH3OH, itself has a nucleophile. So nucleophile is OCH3. So this favor SN1 mechanism. Solvent. SN1 mechanism. So this compound with this reagent form a mixture of these configurations. One is retention, other is inversion. Okay, SN1 mechanism. So this is the correct answer for this reagent. This is the correct answer for this reagent. And this nucleophile is CH3O. That is. So this acts as a solvent as well as a nucleophile donor. Next compound is benzene with CH2Cl. That is secondary carbon. This carbon is also containing benzene like this or phenyl group. This is electron withdrawing group. This benzene is always electron withdrawing group. Presence of electron withdrawing group can have different types. That is, you can usually have SN1 mechanism also important. And depending on the protease or medium, it can also SN2 mechanism. So this can undergo SN2 as well as SN2 mechanism. With this reagent DMF and the nucleophile SN2 configuration is inverted. The nucleophile is OPH, sodium phenoxide. Na plus is removed, here OPH attack. This is the configuration and the product. It can be acted upon by water as because present SN1 with strong electron withdrawing group. We get undergo SN1 mechanism. SN1 mechanism is that is nucleophile is OH. This is a OH2O provides nucleophile. OH, here configuration is mixture, retention and inverted. SN1 mechanism. This compound with this reagent will give a product like this. The same compound with this reagent will give a product like this. And final one here that is nitro group is there, F group is there, benzene, and here carbon is CH, Br CH. It is secondary carbon, CH is there, and very strong electron withdrawing group. That is NO2 is there, benzene with NO2 strong electron withdrawing group, very strong electron withdrawing group. If that is the case, what is that actually with presence of this? That is a strong nucleophile on this orbit, DMF, and produces what kind of power? SN2 mechanism only. Here SN2 mechanism is it is replaced by the nucleophile SPH. Geometry is inverted, dotted line here. Solid line, thick solid line, thick dotted line. This is the correct answer. This is already asked in the IIT examination. This question. And one more important. Now I said right, this undergoes usually this pure, that is methyl, undergoes SN1 mechanism, that is SN2 mechanism. That is pure, this one always undergoes SN1 mechanism. SN1 mechanism, SN2 mechanism. Now we see that this is a methyl group, that is this is the one methyl group. Here one H plus is replaced by CH3COH, that is electron withdrawing group. This is entire thing. So this is actually what is that will favor more than this even. If H is replaced by this carbon is this undergoes SN1 mechanism. It favorites the SN1 mechanism more than this. That is the order of SN1 mechanism. This is highest order, next order, and next order. This becomes secondary. Primary carbon will be CH2. So these are the examples under this. And in this case, if the carbon here, in all these cases, carbon is what is that? One carbon, only one chiral carbon. There are different groups, only one chiral carbon. If involves. If there is only one chiral carbon, we expect only two types of geometry. They are called enantiomers. One chiral carbon. Carbon with four different groups. That is, one chiral carbon produces two enantiomers. That is R and S. If the molecule contains two chiral carbons, two asymmetric carbon, the geometries are diastereomers. Usually this kind will produce enantiomers. And let us see one example, diastereomers. One example, right? Here also the reactions. What is the diastereomers it produces? Alright. compound is carbon. There are two chiral carbons, asymmetric carbon, connected by four different groups. This group, this group, this group, the entire group. These are the asymmetric carbon like this. This group, and this group. Cl is there, attacked by water. That is SN1 mechanism. Usually SN1 mechanism, water. So with this SN1 mechanism, we have two isomers. Two isomers. The two isomers means that is Cl and Cl, same configuration. It is inverted configuration. Inverted configuration. You get now, these two are diastereomers. This is one diastereomer, this RR. Configuration, it is based on this. That is higher group. That is this group and this group and this group with respect to this bond. That is right direction. That is clockwise. And this also, this higher, next higher. That is Cl. So this also right. This also right. This carbon is right, but this carbon is left. That is like this. The priority. So carbon with R. This carbon configuration R in the reactant. In the product, here R. That is R into R. Here another configuration is R. Here S. R into RS. So we get the two different configurations. That is RS. That is RR. So they are called as diastereomers. So this kind of reaction gives this kind of geometrical isomers. These are called diastereomers. Diastereomers means the similarity what is that they don't have what is that mirror images. But in enantiomers, the mirror images, they are one is the other mirror image of the other one. But here it is not the mirror image of this either way. And the image this is non-superimposable on this. Enantiomers, mirror images non-superimposable. But diastereomers, no mirror images and no superimposable. That is called as diastereomers. But those molecules contains two asymmetric carbon atoms. More than two asymmetric carbon atoms or more than two chiral carbons produces diastereomers. Only one chiral produces enantiomers. That is a kind of geometry we get a SN1 mechanism. This also is all important in the examination. So with this, let us finish off. Thank you very much.